Good afternoon and welcome to this talk by Dr. Edmund Hunt. Really pleased to see that some of the people who were at the robotics panel this morning are joining us this afternoon as well. I'm Dr. Catherine Blackwell. I'm the head of the Faculty of Engineering Industrial Liaison Office. As some of you will be aware, this talk is part of our Faculty Research Showcase event, which is running all week long, and it's aimed to demonstrate the breadth of the research capabilities we have in engineering at Bristol. We want to provide a stimulus for conversation and hopefully stimulate some future collaborations. So thank you for joining us today, and I hope that you find the session both interesting and thought-provoking. I'll now hand you over to Edmund, and his talk is Swarm Robotics in the Real World.
All right, thank you, Catherine. Hello, everyone. Thank you for coming. I hope you've been enjoying the showcase so far. And as you can hear, I'm a little bit croaky today, but hopefully I'll still come through loud and clear. So indeed, I'm happy to be with you to give you this talk then about swarm robotics into the real world. How can we take swarms of robots and put them into real world situations where they can do useful things for us? So start with a quick overview of my talk, the things I'm going to get into. Begin by just thinking about, well, what is a swarm? A swarm in nature or a swarm of robots? What distinguishes it? And what is not a swarm of robots? And then this question, how can we make them effective in the real world? And I've got these particular themes to my research that I'll go into briefly, and we can think about more in the questions and answer. I'm looking at how we can introduce a certain amount of diversity, behavioral diversity among the robots to improve their performance. This is known as functional heterogeneity. Behavioral flexibility or plasticity, how can they adapt their behavior to the changing real world conditions? How can we make robots aware of hazards or risks in their environment? That's an important part of getting them ready for the real world. And how can we make swarms safe, both for their human users and of course safe to themselves so they're not bumping into each other and damaging each other. And then I'll finish by talking about the project that I'm working on with swarms, which is deploying swarms for monitoring the environment. So what comes to mind when we think about swarms? What do you think of? Well, think about things in nature typically. So you might think of a swarm of locusts, a swarm of honeybees, flocks of birds, even something like a slime mold, army ants. And, human beings, because when you have large numbers of agents, large numbers of individuals come together, the key things that these different examples have in common is that you get emergent group level behavior. And that's regardless of what the individual looks like. So you think about humans as individuals, we're very sophisticated cognitively, but actually when we're in a crowd, we can be part of a moving mass, as shown in the picture, part of these collective dynamics that are emergent when you get a lot of individuals together. So what unites all these different systems? Well, it's this concept of self-organization that I'll explain briefly. This is really the key idea, I think, when it comes to swarms. And this is a great book on self-organization. So you see the different examples on the cover, like the butterfly wings or the honeybees. The key thing that they have in common, whether it's pattern formation or their social organization, it's the fact that the organization occurs through internal interactions within the system. It's not imposed from the outside. For example, in an ant colony, the workers are deciding at each instance what to do, making their own judgments. They're not taking orders from the top down from the queen. She's not a supervisor telling them what to do. And this is unlike human systems, which have a hierarchy, where orders come down the chain of command. When we talk about self-organization and swarms, the order, the capabilities of the swarm, they come from the bottom up. They come from local interactions, individuals interacting with their nearest neighbors and with their local environment. So an example, a really nice example of this is flocking, right? So you see these beautiful starling murmurations in the sky. Of course, this wouldn't be possible just with a single bird, but when you have really large numbers together, you get these beautiful emergent patterns. And people have looked at these for centuries and wondered how it was possible to see these patterns. And actually, as scientists, we can explain these through the individuals following simple interaction rules. Very simple rules that they follow can result in these patterns. And actually, in 1987, a chap called Andy Reynolds developed his model of Reynolds flocking, or Boyd's, and he boiled it down to 3 simple rules. So if the birds or the simulated agents, they first of all keep a minimum separation. If they get too close, they push each other apart. If they get too far apart, they want to move back together, so that's cohesion. And then alignment. If they will want to tend to stay pointing in the same direction. And you take these 3 rules together and you get this emergent flocking behavior. So it's quite neat to watch. And this has been used, for example, in the movie industry, in animation. It looks very lifelike because this really captures the essence of what's going on. So you see these flocking boids. And this is a nice example, you know, the movie The Lion King. When they filmed it, or animated this scene of these wildebeests coming down the side of the mountain, you know, it's a very hard thing to do by hand, but by using these Boyd's simulations, you can create realistic flocking patterns. So this is the kind of thing we want with our robots, to get large numbers of robots working together. Why would we want to do that? Well, there's really 3 main advantages proposed for swarms. The first is its scalability. Okay, because individuals are only using local sensory information, and they don't necessarily need a memory of what's going on, they're following these simple rules at each point in time. It's very scalable because it's not being controlled from the top down. So you can just keep on adding agents into the swarm because they don't need to know what's going on in the global overall state. They're just looking at what's in front of them. It's also imagined to be robust. You know, if you lose a robot, if you lose an individual, it won't affect the performance overall very much because they're not dependent on single individuals. Okay, and it's also imagined to be flexible because individuals are responding to their immediate environment. You know, as the environment changes, their behavior will change. And this gives them great flexibility, supposedly, to adapt to changing task demands. So what's been some of the swarm robotics research done so far? Well, it's really been a field developed over the past 20 years or so, and it's been mostly laboratory based. So one of the first projects was called these S-bots, short for swarm bots, and they have these little grabber arms. So what they can do then is grab onto each other and form these chains. And in that way, they can accomplish things like crossing gaps, and as you see here. Another very well-known example in recent years is the kilobots, kilo, because you can build literally 1,000 robots. But they're extremely simple. You see here, they've got these little tripod legs, 2 motors to vibrate around and move. They're good for exploring kind of conceptual ideas. So I'll show you, you can use it for sort of pattern formation. You can get your robots to come together and form you know, like this starfish pattern, for example, but they can't work in the real world because they're so simple. Another example would be these Termes robots inspired by termites, right? People are excited about the idea of using swarms of robots to construct buildings. Wouldn't it be great to get robots laying bricks, just like termites build their huge mounds? Another example known as the COCO-RO project, Collective Cognitive Robotics, an underwater swarm. And they've got these flashing lights and they can look at what their nearest neighbors are saying through the flashing lights and coordinate and sort of flock together, school together underwater. But what all these examples have in common is that they're in controlled environmental conditions. Wouldn't necessarily do very well in the outside world. But perhaps we're at this point now, a tipping point, where people are thinking about taking swarms into the real world. So I'll just give you a couple more examples. There's the PipeBots project, which is ongoing at the moment. And there are people at Bristol involved in this project. And that's the idea that you could put robots underground to inspect pipe networks, sewage pipes, for example. And the real great advantage of swarms here is because they don't rely on instructions coming from the top down. They'll do very well in pipes where it's hard to communicate messages to the robots, right? The idea, conceptually at least, is that they should be able to inspect the pipes and find leaks, for example, and maybe even repair them themselves. And that's a project that's active at the moment. And of course, there are people in the defense industry interested in swarms. DARPA, the US defense industry researcher organization, they're thinking about how you could use swarms of robots to gather situational awareness in an environment, go out and gather information. But is this really a true swarm? Because it's very closely controlled by human users. So this takes me on to my point now, and this is the challenge of getting swarms into the real world, because think about, well, what is not swarm robotics? Because there's examples of having multi-agent systems, but they're not strictly swarms, because they might rely on centralized control, might rely on being very closely supervised by a human user to send instructions. They might need access to the global state of the swarm, what all the other robots are doing. They might need to know what the total group size is, for example. But the trouble with this is it won't scale up in the way that a real swarm would be able to. So if you're relying on a base station, for example, you want to add in another robot, you might encounter communication bottlenecks, and it just won't work. So it wouldn't really be a true swarm. A true swarm would be decentralized, and then you'd be able to scale it up, as much as you like. Because there are these really exciting examples now of large numbers of robots working collectively. So this is the Ocado fulfillment warehouse, where robots go around, they pick up groceries from the different stacks of boxes to get your order ready. But again, that's not really a swarm because it's very tightly controlled from a central computer. Another really nice example where you're seeing large numbers of robots is in these sort of, what would you call them? Digital fireworks, if you like, okay, where people are using drones to light up the night sky and form beautiful patterns. Again, it looks really swarmy, but is it really a swarm? Perhaps not, because it's really tightly controlled from the central base station. So the challenge then for real world swarms is that if we're going to see a real swarm, it's got to have this quality of self-organization. And it's going to face these challenges of the environment will be dynamic, it'll be changing. So you might optimize the swarm behavior for a certain set of conditions that works very well in the lab, but you put them outdoors and the world changes, the weather changes, or something even more unpredictable. Maybe there's a thunderstorm, maybe there's a disaster, and they just can't cope because the world is unpredictable. There's noise in sensor measurements, there's uncertainty that they've got to grapple with, and there might be hazards, There are risks in real world environments that robots have got to learn to cope with. And of course, they've got to be safe. You start talking about a swarm of robots, dozens or even hundreds of robots out in the real world, you think, well, gosh, it had better be safe. Not only for the human users, obviously, but for each other. They might bump into each other. So this is informing my research goals that I've been working on. I've been making conceptual and practical explorations of how to tackle some of these things that I'll finish the other half of the presentation talking about now. So one of my major research themes that I'm thinking about is, you look at a colony of ants, dozens, hundreds of ants, and then they look pretty much like they're all the same, but they're not the same. That's the intriguing thing. Even if they're following fairly similar interaction rules, they might have different behavioral thresholds in the way that they respond to information. So in swarm robotics, most of the research that's been done assumes that agents are homogeneous, that they're the same, that would mean. In the world of collective animal behavior research, though, people are increasingly recognizing that heterogeneity, meaning differences among the individuals, is actually really important for the emergent group functions that they have. So, you know, you take something like a hive of honeybees or a colony of ants, they look very similar, but there's behavioral diversity. There's also morphological diversity in the animal kingdom, which morphological meaning the shape, the body plans of the animals, and that's more obvious. You know, so these are army ants here, and you see they have different castes. So there's different sized workers, there's soldiers, and that's the queen. These morphological differences are really important to the way that they function. And some people have thought about this. They've made some initial look at examinations of it. This is the Swarmanoid project, which had some fun with 3 different kinds of robots. But there's not really been that much thought about how can we tap into the power of functional heterogeneity. So an example of where functional heterogeneity is really important with behavior would be in nest thermoregulation in honeybees. So honeybees have this behavior where they, of course, just like we want to maintain our human body temperature, they want to maintain the temperature of their nest. And what they do is they have this fanning behavior where they will flap their wings to get an air current flowing. You know, they'll do this in the entrance of the nest to try and get a cooling flow of air moving through their hive. But the intriguing thing is that each individual will respond at slightly different temperatures. You know, just like you and me, we have different ideas of what is hot and what is too hot. Honeybees are the same. So they will have their cooling behavior triggered at different thresholds. And what we see, in fact, is that when there's more diversity in these thresholds, because there's more genetic diversity within the colony, actually they do better at regulating their temperature. It's more stable. Because if you imagine a distribution of behaviors, a distribution of thresholds, it's a bit like your thermostat. You know, if the heating comes on gradually, so the ones that are most sensitive start flapping their wings, and then the ones that are sort of middling sensitive start flapping their wings, and the ones that are least sensitive start flapping, it comes on gradually, the cooling behavior or the heating behavior. If it's you know, imagine your heating system at home, that's actually much better at keeping the temperature stable. Whereas if the cooling or the heating all comes on at once, they all have their behavior tripped at once, that you will tend to overshoot, right? And you'll have much more unstable temperatures. So this is an example of where diversity in thresholds, diversity in behavior can be really important to real world behaviors. And there's many other examples that I could go into where diversity within a swarm is actually really, really important for their group performance, whether that's making decisions collectively, exploring the environment collectively, collectively foraging, and so forth. And an aspect of my research is looking at this area of biological research called animal personality studies, because when it comes to behavioral diversity, a lot of people now talk about this in terms of animal personality, which are consistent differences that individuals have. And there are some of these major personality axes that have been applied to the way animals behave. And you can kind of boil it down into these major axes of risk-taking behavior. Individuals will vary in how they take risks, whether that's boldness or shyness. Exploratory behavior, whether they seek novelty or avoid it, their activity levels, their sociability, their aggression levels. Thinking about how we could have diversity like this in a swarm could actually make real-world robot swarms much more capable of dealing with challenging real-world environments. And indeed, you can talk about collective personality as well, and you might want your swarm of robots to show different swarm-level personalities. A related idea that I'm looking at, which is linked to this idea of diversity, is actually plasticity. Okay, because if you've got a distribution of thresholds, that distribution might work very well in one environment, but what you might want is for that distribution to be able to shift and adjust in a different environment. you know, when the world changes, you need to change your distribution of behaviors within the swarm. And the way this works in biology is through something called phenotypic plasticity, which is the idea is that one set of DNA instructions, which is your genotype, is actually capable of producing a range of different traits depending on the environment. And the traits are the phenotype. And the way you can describe this is through these kinds of diagrams that I have here. This would be called a developmental reaction norm. So you see in the first example, it's flat, it's horizontal, there's no plasticity. The environment changes, but the traits stay the same. And then the second two diagrams, you see there is plasticity, the environment changes and the traits change. So what I think is really important, going hand in hand with the diversity, is to have the plasticity, the phenotypic plasticity, if you like, to adapt these distributions depending on the changing real world conditions. And I've written a bit about this in relation to inspiration from nature. So here are some examples of animals. So in picture A, you have social spiders, which live as a group. They have flexible personality distributions, right? So you have most individuals are shy, a few individuals are bold. That helps their collective predation behavior. But what then they're able to do, depending on the level of food or risk from predators in the environment, they will shift that distribution of shy and bold in order to optimize their collective performance. Example B, that's a toad there, a cane toad, you know, is an invasive species in places like Australia. The reason it's such a successful invasive species is its plasticity. And that's in respect of its physiology, the way it can cope with different temperatures. So it can move from temperate areas to hotter areas, because it can basically adjust its internal body temperature and cope with that. That's an example of physiological plasticity. And C there is an example of bacteria. So the bottom half of the pane, this is what they look like normally, but under stress, say under higher temperatures or when they're trying to be eaten by some other bacteria, they do this thing called filamentation, where they will form these long lines like this, and that makes them harder to eat. And that would be an example of morphological plasticity. So there's all these different kinds of plasticity that I think can give so much sort of inspiration to engineers thinking about how to get plasticity in their robot systems. I also mentioned D&E here. So these are clonal organisms. These are certain species of ant and fish. Even though they're genetically identical, which is quite unusual that they would all be genetically identical, they're not behaviorally identical. So to me, a really good place to look would be these kinds of organisms, because despite having the same genotype, their phenotypic plasticity is such that they can adapt their distribution of behaviors within a social group to work together effectively. So these are the kinds of organisms that I'm looking at. It's really good to keep an eye on the biological research as an engineer. So let me give you an example of some research that I've done that's kind of been informed by some of these concepts. Imagine you want to put your robots into a hazardous area. You know, you think of an example like the Fukushima disaster, where you really want to get some information about what's going on there, but it's dangerous. And you don't want to destroy a lot of your robots at once. You want them to be able to manage the trade-off between risk and reward, the risk for the hazards, but then the reward of gathering the information. Imagine that you want to build chains of swarm robots that can pass information down the chain and then feed information back to you. What you might say is, well, I'm going to have some bold robots that are going to take the risks, and then some shy robots that will stay out of harm's way and focus on the kind of the core base area. Okay, and we explored this idea using these kilobots that I mentioned earlier. So just briefly then, it's a very simple example of how we could do this in a self-organized fashion, which is to say the truly swarm way of doing it, using the self-organization. To build these chains, they adapt their boldness levels such that if there's a large number of robots around them, they increase their boldness, whereas if there's only a few robots around them, a lower density of robots around them, they will tend to reduce their boldness. And what this allows them to do is to sort of take risks proportionate to the overall state of the swarm. Because if there's a lot of robots around you, that gives you confidence, like, well, I can afford to sacrifice myself, if you like, by doing something more risky. Whereas if there's only a few robots around me, I better play it safer and stay close to the base. So let me show you a little animation of what this looks like. You set this kind of simple algorithm off, and what you see is after a period of time, they will self-organize themselves into groups of medium shy, very bold, and shy robots into these three different categories: shy, medium, and bold. Then the interesting part about this is that if some of them are destroyed, as in this example, if you start with 128 and then destroy half of them in simulation, you see the proportion of shy robots will steadily increase, halve it again down to 32. They will kind of cut their cloth according to the size of the swarm, if you like, and adjust how they're taking risks. So this is an example of the behavioral diversity, the personality, but also the plasticity, where they're able to adapt this distribution of bold and shy according to the dynamic changing environment that they find themselves in. A couple of extra things that I'll just mention. An important part of getting swarms that are riskable into the real world is having them be aware of the risks that are in front of them, as in the preceding example. We've thought about how we can use some existing methods from finance to calculate risks, because obviously in finance, you've got to manage risk. It's a core part of the job. And they use a metric there called value at risk. Okay, so if, for example, you've got the stock market, like the famous FTSE 100 index, if you look at the returns over a period of, say, 10 years, as this graph shows, most of the time you'll have quite small positive, negative returns, which is the peak in the middle here. Occasionally you'll have very high returns, and sometimes you'll have very negative returns. You'll have a bad day on the stock market. What the value at risk method does is say it looks backward at a chunk of time, say 2 years, and it says, well, let's take the worst 5% of returns and use that as our assumption of how bad the risk could be. Over the next day, I wouldn't expect to lose more than this money 95% of the time. Okay, depending on how conservative you want your risk measure to be, you could look back to even more negative returns and say, well, let's look at the very worst 1%, for example, depending on what kind of confidence you want to have in the level of risk that you're facing. So we applied this to some simple swarm robot simulations. So if you imagine there's hazards in the environment, which is the diagram on the left, and some positive reward in the environment, which is the diagram on the right, that kind of gives you your profit and loss. And so the robot will kind of move around, gathering profits, but experiencing losses from the hazards. It can use those inputs to calculate a value at risk. And then it can use that value at risk to make decisions. And specifically, it can use its value at risk limit, which is set by the user, to warn other robots nearby if its VAR limit is breached. So you remember I said the thing about swarms is they're self-organized, they're based on local interactions. It can warn its nearest neighbor, oh, I've breached my VAR limit. I've experienced a really rough patch here. And what we find is that when they're able to broadcast these warnings, then indeed the swarm does better, because they can, the other robots can speed up and move away from that area. So having an awareness of risks and hazards in the environment, operationalizing this by having these risk metrics, again, is, I think, an important step forward to real-world swarms. And again, you might have diversity, you might have heterogeneity in these risks limits. And this might be useful when there's certain structures in the environment. So imagine instead you have like a barrier, this yellow line here, a barrier in the environment, which is very hazardous, like a really hazardous radiation patch. What you might do is you might say, well, I'm going to have some shy agents with low VAR limits and some bold agents with higher VAR limits. And And in that way, the bold agents will endure the kind of the pain of going through the barrier, and in that way manage the trade-offs of saying, I want my robots to explore, but I don't want them all to get destroyed. So these are the kinds of things that we're thinking about. So finally then, swarm safety that I mentioned. Recently we published this idea of saying, well, let's have a checklist before we deploy these swarms into the real world. It's really important to think systematically before we really put large numbers of robots into the real world. So we came up with this list of 10 points of things to think about before deploying your swarm into the real world. And one thing I would emphasize is that, you know, this idea of emergence. When you have large numbers of agents working together, you know, new things happen. That's the advantage of robot swarms, biological swarms. It's the emergence of new capabilities. But then this is also a source of risk and potential safety concerns, right? Because perhaps your emergence of, say, collective decision-making won't work in the way that you want it to work. And as a result, you know, your swarm will fail. So you've got to think carefully about how emergence might lead to hazards, and indeed emergence might just not work in the way you want, so it won't be capable of achieving the task. So we've kind of thought about this in a fun way, thinking about how could we deploy some robots into Bristol Harbourside and all the different concerns and considerations that you might want to work through before making it a reality. I'll just finish very briefly then, talking about what I'm trying to do to bring all of these ideas together. In my current research is thinking about how can we use swarms of robots to gather information from the environment for environmental monitoring, whether that's monitoring for pollution or monitoring for security, just to check that our environment doesn't have anything unusual or anomalous going on. And, you know, it could be applicable to the nuclear industry, where there's hazards there, environments that we want to monitor. Could be applicable to something like a data center, where you want to check that it's running within normal parameters, or it could be applicable to something like agriculture as well. So I'll show you a very brief video. Bristol University has this test facility called Fenswood Farm, which is being used for robotic field trials. It's great to have this real world outdoor space. And this is a simulation that I've developed to kind of show off what I'm hoping to do in the real world, thinking about having swarms that work alongside other people, monitoring a facility, gathering information, you know, monitoring for things like pollution potentially, anything unusual that might be going on. It would be capable of working indoors, but also outdoors as well. Capable of working in restricted environments like down a tunnel. And then it comes to this idea that I've mentioned of the functional heterogeneity, having different distributions of behavior. So in respect of risk appetite or boldness, for example, robots could have it all set the same, or you could have a skewed distribution where most of them are shyer, few of them are bolder, and together they're able to grapple with unexpected hazards in a way that manages this trade-off between gathering information but not doing anything too dangerous. Perhaps calling in human users for help rather than investigating it themselves. Okay, this is just a quick video. You know, we do want to do this in reality with some real robots that we're developing at the moment. So that's all that I want to talk about today, quite quickly. So just to recap, talks about, well, what is a swarm of robots? Comes down to this idea of self-organization. How can we make them effective in the real world? Well, I've talked about this idea of personality, phenotypic plasticity, this idea of using VAR metrics for risk awareness, thinking about perhaps a checklist for safety. And my real world goals are toward environmental monitoring. And there's a lot of applications there where swarms could actually be really useful in the not too distant future to give us information and make our world more safe and secure. So thank you for listening, and I'm very happy to have some questions now.
Edmund, thank you very much for that presentation. We do have some questions for you. So the first question is, how would you calculate the VAR using real world sensor data?
Yeah, so I think as I talked about in connection with finance, it comes down to this idea of profit and loss. So it will depend on your scenario and what you deem profitable and what you deem to be hazardous. So if you're deploying a swarm in relation to environmental monitoring, maybe in a hazardous environment, but you want the robots to explore, gather new information, you might assign a positive return to the mapping of new areas that you've never seen before, adding new bits to your map, new jigsaw puzzle pieces that you're adding on, and you might assign loss to exposing the robots to some damaging radiation hazard, for example, which is something that could be objectively measured. Radiation is something that can be measured as a physics-based quantity, using a radiation sensor, and you want to try and minimize that exposure. So you would want to put that profit and loss somehow on the same scale, which would require you to think about, how am I exchanging my profit with my loss? What amount of information do I want to get in return for 1 unit of radiation exposure? And then that comes down to the user kind of deciding, well, how much risk do I want to put my robots through? But the really exciting thing, I guess, or one of the really exciting concepts with swarms is, I talked about robustness, that you can lose a few robots. The flip side of that is that actually you might actively want to be able to take risks. There's an idea of expendability, or attritability would be a related concept, that actually, because your robots are relatively simpler, relatively cheaper, if you have 100 of them, it's not the end of the world if 10 of them get destroyed, okay? It's not going to blow the budget to replace them at a later date. So having that large number of robots allows you to, let's say, approach these hazardous environments, for example, with a different mindset of saying, like, yes, well, I am willing now for some of my robots to be destroyed because there's really valuable information that I want to get here, and of course, in a kind of search and rescue type scenario, we're very much willing to risk our robots because there's human lives on the line. But if it's maybe something a little bit less urgent, mapping some danger zone, you might want to think more carefully about where the balance of these two factors lies. But the way I see it with swarm robotics, it kind of opens up the doors to a whole new calculus, thinking about how we can use robots in these kinds of situations.
Thank you. And that leads into the next question, really. You mentioned about how environmental monitoring is one of the things that particularly interests you, but are there any other real-world applications that you'd really like to look into and explore in more detail?
Right. Well, I think environmental monitoring itself can encompass a lot of different things. I've talked about radiation in respect of like monitoring hazardous environments, but it could be looking for things like pollution, detecting pollution sources before it causes too much damage to the environment. But then I suppose related to that, people have talked about the idea of using swarms of robots to do things like then clean up the pollution itself, right? So not just to identify it, but then to fix the problem as well, which would be really exciting. So you take a problem like an oil spill in the ocean, or the big patches of garbage that swirl around the Pacific. And people have talked about how you could use swarms of robots to basically try and engulf these patches of oil or plastic and kind of herd it together into something that you could come along with the ship and scoop it all up. So that would be quite fun as well. Another exciting thing you could do with swarms in dangerous environments would be for the emergency services. So people think about using swarms of robots for firefighting, for example. So you think about a warehouse. You can have these big industrial estates, big warehouses. Often firefighters looking at that will have no idea what the configuration of the building inside will look like, or where there might be some dangerous materials that could explode, or very unpredictable. if you had a large number of robots, you could send them in, they could map it out for you, they could pinpoint these hazards, potentially find people who then, will have a route to find their way out again, follow like Hansel and Gretel, like the robots might light the way up in the smoke-filled room. So there's a lot of exciting things one could think about, which is why I think swarm robotics is such an exciting time for the field.
Absolutely, and thank you very much for giving such a great overview of the field of swarm robotics. We are at the end of our session, so I will bring it to a close. Many thanks to all of you for attending and for the questions, and thanks to you, Edmund, for your presentation. In the current climate, unfortunately, online is really the only way that we are able to do this showcase activity. Usually we would like to do it in person and hope that we can do that again sometime. But we appreciate that this virtual method doesn't allow for the amount of interaction that we would really like. But if you have been, if what you've heard today or throughout the week has captured your interest, then please do get in touch with us. The Industrial Liaison Office is part of the Faculty of Engineering designed to help connect you to academics and students. And we'll be sending out our contact details after the event, so you can get in touch with us and you can get in touch with the speakers through us. So do get in touch if you want to explore any of these things further. But in the meantime, thanks very, very much for attending and have a good afternoon.